In this video, we'll generalize what we did in the last video a little bit more. Now we have two sources instead of just one, and at time 0, we flip the switch from Vs1 to Vs2. So drawing a timeline, let's use this to figure out what happens. For t less than 0, we have a circuit that looks like this. T greater than 0, it looks like this. In steady state after a long time, we can see that Vc0 equals Vs1. And similarly, in steady state after a long time, we'll have that Vc of infinity is Vs2. Now we want to see how we get from one to the other. So we're trying to figure out what Vc of t is. So we'll sketch the circuit after the switch is flipped. Now writing a KVL equation, where here I'm pointing out that this is ICR. We can use this to write, and then putting it in more of a standard differential equations form, we'll have, and then using alpha, we'll simplify it a little bit. Now we'll use that integrating factor from before. And I lost some subscripts, so I'm going to put in here Vs2, make it right. We recognize that this side is that. Now we're going to integrate over, we'll call it t prime here, I guess. So t is going to get replaced by the dummy variable t prime. So we can integrate from 0 to t. We have this. Here's what we have on the left-hand side. On the right-hand side, and then expanding these out. Finally, we can multiply by the inverse of our integrating factor and isolate Vc of t. I'm going to write this like this. And then just rearranging it once more, I rearranged it like this so that you can see a couple of things. At t equals 0, that exponential goes to 1. So we have Vs2 plus Vs1 minus Vs2. So we have, and then at t equals infinity, so we're just checking the range, the extreme limits here. That exponential goes to 0, and we're just left with Vs2. And looking at the picture that we drew earlier, we see agreement as we compare with the previous results. Vc0 is Vs1, Vc infinity is Vs2. And we've done this in a very general way. We don't know whether Vs1 at this point is bigger than Vs2 or Vs2 is bigger than Vs1. So you could have a condition where, say, Vs1 is 0 and Vs2 is positive or negative, in which case you're charging the capacitor. So let's just sketch that. And notice here that in this case, Vs1 minus Vs2 is negative. So you should expect to see a negative exponential decay. So that's what it's going to look like here. And then we'll mark a 5 tau, because that's where this natural response or transient ends. We could have another case where Vs1 is greater than Vs2, and maybe both are greater than 0. And here are Vs1 greater than Vs2, so this parenthetical term is positive, so we'll see a positive decaying exponential, calling some term out here 5 tau. So we've just treated this in a very general way, and you could see what's happening here where we're going to highlight our VS2 here as the final state. This is the initial condition. And then we'll often use 1 over alpha with tau as a time constant or characteristic time. So in the case of an RC circuit, you'd have tau is RC. Why? Because if you look where we defined alpha, then this is 1 over tau, and tau is RC. Okay, so that was the general treatment.